Hello and welcome back to another video C on my C++ tutorial series, and welcome to Pointer Madness. This video is all about pointers and how to use them and how to do magic stuff with them. Basically what we want to do is we want to write the INIX. INIX is going to be an advanced version of our INI parser building up onto our INI parser. And this video might be a bit longer because we are now writing a full new feature that is going to be way more usable actually, but also way more complicated. And this video is just to revisit pointer and to show you how you would do stuff in C before we then gonna clean up all those things that we don't know about C and then transition to C++. So this is like one video where we are writing C code. Next video we're going to write C code as well, and then we're going to transition over to C++. So Pointer Madness today. Okay, so what are we going to do in Pointer Madness? In Pointer Madness we're going to write a better version of our INI Explorer and our INI parser. Well, our INI Explorer currently is not really doing something amazing. The only thing it's doing, it is enumerating all of the data. And this is actually how some libraries run. If you're finding a parser library, there are two versions of parser libraries. One parser library is like that one. It's basically just calling a callback every time it finds a valid value. And this is how many parser libraries run. And I don't know why there are special keywords on how this is called, but I forgot them. Maybe I can look them up quickly. All right, I found it on the internet how it's called. It's called DOM and SAX. There is SAX. This is one what we already had here. SAX is simple API for XML. Okay, it's Scalaf XML, but simple API called SAX here. X stands for XML, but however, so we would have XI, simple API INI. Is basically parsing something like we had this start object, key hello, string, key true, key boolean, key null, key. So basically it reads from top to bottom and it is noisy and output everything that happens, which is what we done. We basically found a section, we found a key and we found a value and we outputted this. Simple API, we just continuously streamed out what we got. And this is like simple API, called simple API. However, what's also available is something called DOM, and DOM stands for Document Object Model. And as it's already telling here, it is an in-memory representation of, in this case, JSON. In our case, it's going to be INI for query and manipulation. So in our case, we're just going to query it. We're not going to be able to manipulate it, but it's going to be able to query it. So the idea of a DOM model is that you don't getting called for everything it founds. It's more, the idea is more that you kind of like say INI data equals parse, and then you can say something like get value for section and key, and then you would get the value or a null pointer if it was not able to find this. So we are kind of like parsing that, storing that in some data structure, and then you can dynamically require some data for that. And that's basically what we want to do here. So we had SAX here, so the SAX API, I'm just going to call it SAX here. And now what we want to add is the DOM API. So I'm just going to say this is going to be SAX here, SAX API. And what we now want to do is we want to have a DOM API. And for that, I'm going to create a new header and a new C code for that so that we can get used to having multiple of them and have this nice structure. Now, how I'm going to call this? We're going to call this INI. Do I want to really call this DOM? I would love to call it INIX actually. So I'm going to call it INIX. I can call this however I want. So INIX is going to be our advanced INI stuff. We're of course going to need our INI API because we also need to export this. And I'm also going to include my INI parser because we want to build upon the parser to be able to build upon what we had. So first of all, what I want to have is I want to have these functions going to be the same. I want to have the same functions here. Now, basically what I want to do is I want to copy them and I want to paste them in here. So these are going to be by default the same. The only thing that's going to be different is they are not requiring a callback. That's not required. We don't want to have a callback here because what it should do is it should output us some metadata. So now what is the metadata it should output? Well, actually what we want to have is we want to have a struct that contains the data on what we found. So we want to have a struct here. Actually, I want to have type def struct here, and I want to call this struct INI. Just call it INI data. And the output of that parsing should be a INI data pointer. So allocated INI data that has been correctly initialized, and if we had any issue and we didn't have something, we can return a null pointer because it has not been used. So we return an ini data pointer if everything went fine. Now, I do need to rename these functions so that they are different than the functions that we had previously, so that we don't get name clashing and have the same name twice. That's just going to append an X here, so it's ini X. It's going to be our advanced library. Now, these are the two basic functions, and we should get started by just writing them. Now, one thing is important. If we are creating this ini data as a pointer, it's obviously created on the heap. If we don't have any memory associated to that, we can't return a stack pointer if it's getting destroyed. So we need a function to close it. So we're going to have a function void ini API ini X close, and this one is getting a ini. Actually, let's call this ini X data as well. ini X data, and here also ini X underscore data pointer. Actually, we can have this one const because we don't need to modify this pointer, and we're going to call this one data. So closing the data like that. So a void function to close it. All right, so to get started, we first need to see what we can do here. Actually, I'm currently, but do I need this function actually, or do I don't need it? I don't think that okay, we're gonna see how we implement this in a second. Let's quickly first create the source file for that. It should create this automatically. Let's, if I hover over that and click the button here, create definition of ini parser in inix.cpp. It's actually trying to create a C++ source file. Okay, so we need to rename this file. By default, it's Visual Studio just like C++. So let's F2 in here and rename this to ini.c. Okay, so right. So let's first remove everything that is here, and let's quickly return null so that we are ready to roll. Now I also wanna create that one in the .c file, and I also wanna quickly replace this with null to get started, and also that close one. I also want to quickly replace that one. It tries to return something odd here because it doesn't know what ini API is. This is just what you get by writing this like that. Now, one thing that we need to do is we always need to have something in here, so I'm going to add a dummy integer in here very quickly so that we can use it and don't get errors here. Now let's go back to ini X and try to implement this. So I told you that we implement that from the stack, so we need to use malloc and free here. So I want to quickly include the stdlib.h header, which is going to give us our malloc functions. So first, let me quickly check if data is valid. If data is valid, we're going to do something. We're going to do some cleanup. To do cleanup, currently we don't need to do some cleanup, but we're going to need some in the future because this is called pointer madness. And of course, pointer madness is going to contain madness about pointers. That's the whole idea of today. So what I want to do here is I just want to free data then, if this is done, because data has been allocated, so I need to free it here. Okay, so now ini.x data is in here. We can free it. We need to implement this. So first of all, we need to think on how we can reuse our SAX API to parse and generate DOM data. Well, basically what we want to do is we want to populate our inix data pointer. We want to populate these inix data pointer every time the SAX API is called. So every time SAX is going to be called, we want to then change the content of inix data. And this already gives us an issue because the ini callback is not aware of our SAX data. Our DOM data on inix data. And this is something that you're going to have many times. Windows supports this, and nearly all libraries that I know and that are written properly and that I like don't support it. What they always support is something called a user data. User data is something that is passed into a callback and can be of any arbitrary type. So you have a user data that you can manipulate to parse your data. So you basically want to add something to that signature. You want to add a void pointer, which is any arbitrary pointer, and I call this user data. So user data is going to be the pointer here, and this is something that we can always pass to our callback. Now, of course, this user data needs to be aware of in here as well, so we need to add it here as well so that we can pass it onto the actual parse function and there as well. Of course, we need to now modify our code here. The user data needs to go in all of the signatures. One above here needs to get the user data, and above here we need the user data, and of course we need to pass this on when we are calling our INI parse here. So user data is going to go in here as well. And now down in our callback, we need to pass this as well. I like to pass user data as the first parameter, but that's something that really doesn't matter. So I just need to pass it on here as well. Now the INIX is working again. Now, of course, our C function is going to fail because we don't have the user data in here. So actually, I should still have this in here. We just need to add it to these functions as well, even though we are not using it. And we need to pass in an additional null, which is basically telling it we don't need our user data. And now everything should work like it worked before. So if I would hit F5, it should build, everything should build. It might not build. What is the issue that you have in here? Okay. Type def struct INIX data. What is your issue? Okay, you're not fine with that. Interesting. Why are you not fine with that? Alright, so that's on something. Actually, like free doesn't like const pointers because const normally means that you don't modify it. But let's. I'm just gonna remove this const here. This shouldn't be the issue that we have. What is the issue? Okay, so syntax error type. So something is wrong with our signature. Type def struct. There could be. Is that solving the issue? No. It would be really interesting if it solves it. Why am I not able to use that here? INIX data is not... it might be, we might need to, if we're using pointers, we might need to switch this over to be there. Yeah. We just need to put the decal spec. This decal spec can be in any arbitrary place before the function name, and if you are using a pointer, it seems that C is not fine with that. C++ is actually fine with that. On C++ this is not an issue. It has actually passed this on in here. It shouldn't be in here, but this one should now build. So actually it should not be here. I don't know why Visual Studio likes to copy this over. Maybe this even solves it. I don't know. In C it's a bit more relaxed. Okay, no, it can't handle that. It's basically because it tries to match the pointer to the decal spec. And if you're matching the pointer to the decal spec, bad things happen. But if you're doing it like that, it should work. Right, okay. So move it there. I know why it's a bit bitchy with that, but that is how things are always working. You can always put this where you want. Most of the time, and remove it from the C file because decal spec is just required once. We don't need it twice. It wouldn't break if I would add this here. I think it wouldn't break if I add the API here again. It is not breaking, but it's fine to have it like that. I would always keep it like that. It's a bit simpler, so you can always alter the API in the header, and I don't know why it's added that one in here as well. Okay, so if I do it like that, it should build fine. Okay, so now the next thing that we need to do is we need to have a custom callback. We need to have a custom callback that we are calling with our INIX data. Now, how are we going to do this? Well, we're going to write, of course, our own callback. So what I basically want to have is I want to have my own function in here. I want to have a void function, INIX callback, because it's our callback that we want to use, which gets an INIX data pointer called data. Then it's going to get a const char pointer section and a const char pointer key and a const char pointer value, right? As simple as that. And that callback is now responsible for parsing our data. Now I want to do this, open this up like that, and now I just need to do some stuff to allocate this. So the first thing that I want to do is I want to allocate the INIX data object itself. So I'm going to have an INIX data pointer data equals to malloc of size of INIX data, and then what I'm going to do is I'm going to later on initialize this to default values. So we might actually want to write this into our own function so that we don't need to write it twice, because we have two of these parsing functions, and we don't want to write them twice. So let's maybe do something like we had this one, this inix close, and we want to have something maybe inix new. So inix new is giving us some new inix object, as simple as that. I can create the implementation in here. It's also not required to be done here by default. It's trying to add this as a C++ pointer, but that's not really what we want. So we can do something like that. And then we can say inix data equals malloc, so that we are allocating data. Then we are going to initialize it. And we're going to return it here. Currently, there's nothing in here. Let's say to do init data, so that everything is correctly initialized. And it's created here, so inix new, it's getting created here, nice and easy. And now we can use the inix new in here, so we can get an inix data pointer data equals inix new, so that we get a new one, and then we want to, of course, also return the new one at some point, and in between we want to call ini parse from file, so the default ini, not the inix, just a normal, please. Ini parse from file gets the file path, the log file path. Now it needs a callback, which is on our inix callback as a function, and the user data is going to be the data itself. If I add these, I'm basically going to call my callback with my data that I just initialized, and that's everything we need for the other function as well, just that we have the ini data in here, and we are not parsing the ini data from file. We are parsing it from the ini data, so that we support both of them, still calling the same callbacks, still the same user data. And now we basically invoked our normal ini SAX parser from our DOM parser with our own data. Now the only thing that needs to be done is in our callback, we need to properly populate this data with all the info that we get here. And the first thing that we need to do is we need to think how we want to organize this. Now, I, of course, have a bit of experience in developing software, so I know how we're going to do this. But I'm going to try to explain this to you in a nice little comment here. We could also use the editor again from Windows, but I think I'm going to write this like that now. All right, so how do I want to build this up? So our root object is the inix data. This is our root, and inside of that we need to kind of like rebuild what we got. So basically our first element that we're going to have here is a section with a name. So a section with an associated name, and each section with a name, we'll do this like that, double arrows, is going to contain a key with a name and a value. So that's kind of like the idea that we have, and each section can contain multiple keys, and a ini data can contain multiple sections. So this is kind of like the structure that we need to try to figure out. And how can we do this? Well, we can do this by writing struct for the sections and the actual keys. So section, we have the inix data, so we want to have something like inix section now, so that we have a section, and something called inix key, so that we can actually store the keys and the values. Now, we could also just call this KV. KV is a bit more meaningful because it stands for key value, and we do store both. So we store a key and we store value. And this is basically how we want to do it. Sections and keys. Now, of course, they will be done as a struct. Now, one thing that you might would want to do now, you would copy that one, paste it 2 times, and call this one section, and you would call this KV. Now, this is totally fine as long as you don't use them with each other. Now, the thing is that we now need a section in the ini data, and we need a key in the section, and this isn't working. If I would now try to use an inix KV here, for example, a KV key here, this looks fine, but as soon as I try to compile it, it is gonna give you a syntax error. Syntax error identifier inix KV. And now you would think, what's the problem here? Well, the problem is that you are using KV before it has been defined here. So actually what you need to do is you need to type def the KV before the section. If I would now build this, it builds fine. Again, the same is going to be here. If I'm going to add the section in here, section, and I will try to build this, we're going to get the same error, and we're going to get even more errors and trash. But if we move this now above here, it is going to work again. If I now build this, works. This is because if we want to use something, it always needs to be there before it. There's something called pre-declaring. You can actually tell the language that there is a struct. So you could say, but that's not really something that you want to do. If you're using this with type def, it's always going to be a bit odd. Just remember that you're always going to start with the lowest root or the lowest leaf of that tree. That is the root, that is the leaf. You always start with the leaf and work above to the root in your data structure. So let's start by the key. I already have this now in order. What is a key going to hold? A key is going to have actually we can do this, no, let's just do it as a char pointer. A key is going to have a char pointer name and the char pointer value. So key value is going to have, actually let's just call it key and value. So KV is going to have a key and it's going to have a value that is then going to be populated with a char pointer. And we're actually going to dynamically allocate all the strings here because we don't know how long they're going to be. We do have some bounds inside of our buffer, but I'm going to allocate them dynamically. You could have this as an array and say we're going to have a maximum number of 255 characters or something like that. However, I'm going to do this dynamically because it's called pointer madness and we want to do pointer madness, of course. Now, this is how a key value is built up. That's really simple. How would we build up our section? Well, our section also has a name, so we would have a name pointer in here. Our actual ini data is not going to have anything. It doesn't have data associated to it. Now, this is how our raw data would look like. We have an empty container with data. The data container is just there to hold everything. We have an ini section. The section has a name, and we have ini x kv, which is key value, which have a key and a value. Now, this is now just representing one element. But what we need is we need to have multiple. We need to have multiple sections and multiple names. Now, how could you do this? Well, you could do an array. I could do and say ini sections, and would say 50. But that one is limiting me to 50 sections. So what I actually want to do is I want to have multiple of them. So what I actually want to store is the first section. So the first section is going to be a pointer to a section. Now, where would be the next section or the last section? How can we determine that? Well, we could dynamically allocate an array and also store a size, something like int section array size, where we basically store how many sections this array can hold. However, then again, we need to deal on resizing arrays and stuff like that, and that's going to be complicated. What I want to do is do something called a linked list. Now, we are not going to completely go into the concept of a linked list. This is going to be, we're going to do this when we are getting to C++. C++ has way better features to modulate these data structures and to explain them and to correctly structurize them. And we're not going to bug you with all the details. But the idea is basically inside the data, we just store the pointer to the first section. And every section is going to have a successor section. So a section itself is going to contain a name and key values, which we're going to do the same as here. So we're going to say inx kv pointer first kv, first key and value. And what we're also going to store is we're going to store the next section. So we're going to have an ini section here, pointer to it, called next section. Now, as you can see, we can use the section because we are inside the section, and I think this should work. If it doesn't work, this is something that is specific to C. And if we're doing this to C, we need to actually name that struct. Now, as you can see, we have an unnamed struct that is defined as a type. I told this to you in the struct video. Now we want to actually give that structure a name. I'm going to give it a name by having an underscore ini section. This is how you do it. If I do it for one, I want to do it as well. This is like something that I tend to do. Give it a double underscore for the struct. And now, as you can see, now the struct actually has a name. And if the struct has a name, you can say struct ini section pointer, and this now should compile. This now compiles because basically the name is introduced after the data has been done, so you need to name it first, then introduce the data in it, and then you need to struct keyword again to kind of like bind this together. So this is how it's then used properly. So struct ini section is going to be the next section. Now, how does that come together? So the ini data itself has a pointer to the first section. Now, the first section is going to be one single struct. Now, I tend to talk about objects, but C is not really object orientated, but what we are really mimicking here is objects. So it has a pointer to the first section object. And the section object itself is defined by a name and the pointer to its first key value pair. And it's also defined by a pointer to its next section. So this is basically now our chain where we're getting to the next section. When can we find the last section? Well, the last section is going to be there as soon as this pointer is null. So if this pointer is null, we know there are no more sections in our list. And this is why it's called linked list, because we are always linking to the next element until we are at the end. So the first one, the kind of like root, the container itself is linking to the first section, to the first element in the list, and each list element is linking to its next element. So it's called a single linked list. And this is the same, we're going to do it with the key value. The key value also going to have a key and a value, and they're going to have a struct inixkv pointer next key. Or next KV. I call this KV, so I want to give this continuous through. So now you can see that this is working quite nice. You can see, all right, we have a first section. The section is going to have a name. It's going to have a pointer to its key value chain. The key value chain, each key is going to have a key and the value, so name of the key and the value of the key, and it's going to have a pointer to the next key. Same in the sections, they're going to have a pointer to the next element in the section. And this is now everything that we need for our data structure so that this comes together. Now we need a few helper functions. I want to be able to create a new key with a simple function. I want to be able to delete a key with a simple function. So let's quickly implement them down here. So inix new, we have that one. Let me actually structure this a bit better. So this is kind of like, this is like our public DOM API. This is now inix data management. We are managing the lifetime of the data, and this are now our internal. Yeah, maybe let's. This kind of like is internal, but it is like internal helper functions. These are this one that's down here. I mean, this is kind of like an internal helper function, but I know it's kind of like living in here. But let's move it down, right? Because it's kind of like internal public DOM API, and yeah, let's just keep this in here. And because I want to be a bit consistent, I'm just gonna remove that one in here as well, so it looks nice. Now, basically what I want to do is I want to have multiple functions for manipulating data. So first of all, I want to be able to create keys and sections. So inix kv pointer, inix new kv is going to be the function. To get a new kv, I'm going to have a const pointer the name. Or actually, let's just call it key and const pointer value. So I can create a new key value pair by giving it a key and a name, and then I'm going to allocate and copy the data around, because remember that we use the buffer inside the normal ini parser in our SAX API that was basically reused every time we read something new. And since we are reusing that, we cannot just store the raw pointer, we need to get the full copy. Now, of course, I want to be able to delete a key as well. So inix, how did I call it? I called this close previously, but I'm now going to call this, I'm just going to call this close throughout. Close kv, inix kv pointer, kv. So I'm able now to create a new one, and I'm able to close one. Now I need the same thing for my sections. So inix section pointer, inix new section. Section is going to have a const pointer name, just a name. We don't need more for the section. And we also want to have a void inix close section to close the section, which is going to get an inix section pointer section. And now we just need to implement them to create them and delete them. Now inix new kv is going to be quite simple. The implementation is just going to be a matter of mallocing something. So I'm going to have an inix kv pointer kv, and it's going to be equal to malloc of size of inix kv to get the size of that, and then I just need to populate this. So inix key is gonna be equal to something, and kv value is going to be equal to something, and then I want to return kv. And now we can actually take one of the string functions. So let's actually include string.h. This is a function that I haven't used for quite a while, so I actually need to look them up. I think I have this probably already open. Let's go to my C ones, and I want to have byte strings here. And we do have a function that can actually allocate and copies a string. So we don't want to have string copy. We actually want to have string duplicate. Allocates a copy of a string. So we want to duplicate the string. This works by this returns a char pointer and takes a const char pointer and duplicates the string. So we can just use string to duplicate the string. Now I basically just paste them in here, string duplicate of my key, so I get a duplicate string of my key, and the same here for value. So I'm going to allocate a dereferencing. Yeah, this could be null, so malloc can always fail, so I want to check that if kv is valid. I'm duplicating these so that it works. And the next thing that I need to do, we have this like next kv, and this next kv is by default going to be set to null. And null basically means that yeah, we don't have a next one. So if you're allocating a new one, if you're creating a new one, it gets the key and the value copied, but it doesn't get the next key because it's not there. Now, of course, we need to implement the matching close function. The matching close function needs to clean up all that mess that we just created. How can we clean up the mess that we created? First, I'm going to check that the kv is valid. Or actually, no, I think we should just assume that it is valid, and this function should never be called if it's invalid. So first of all, key and value, we need to free them. So free key, and we need to free the value, because string duplicated allocated these, so we need to free them so that they have been cleaned up. Now, the last thing that we need to do as well is, of course, free the object itself, so free kv down here. However, there is now one important thing. Now, remember that next kv pointer. What is if that pointer is valid, so that somebody actually allocated another key? So, for example, somebody walked through all of the keys and found the null pointer and then appended a new key by assigning kv next kv equals to our inix new kv function. If somebody used this function to append something to an already existing kv chain, well, if we have another kv in there, we actually need to close this one as well. So if kv has a next one, we need to actually close them as well. So I call this function, this is now called recursion, I call this function recursively on the kv next kv. And this is now gonna infinitely go on. So I like to always put my recursion stuff at the top. So if I have a next key, I'm going to clean this one or close this one first. So this is actually now following the whole list of keys that we have. So for example, if you would have a chain of, let's say, section A, and the section goes to kv1, and that one links to kv2, and that one links to kv3, and that one has at the end null. So basically what happened if I would call close kv on kv1, it would check if it has a next one. Yeah, it's a valid pointer. It goes to kv2, checks if this has a next one. Yeah, goes to kv3, checks if that has a next one. No, it doesn't. It is null. It's freeing the data of that kv3, freeing the kv3 itself. Then it jumps back to kv2 executing. It's done cleaning up or closing kv3. Now it's cleaning up itself. So it's removing all its own members, and it's removing itself. Now it's returning as well back to kv1. kv1 is also done with that block. It is freeing its own key and value data and then frees itself. This order is also important. You need to first free the members and then free the object itself. If you are freeing the object itself, then the debug runtime has already invalidated the memory, and you could go into an access violation, or you're probably going to go into an access violation. So it's always important that you free your internal data first before you're freeing the object itself. So free kv is going to always be at the bottom. And now this basically is now walking the whole chain of KVs that might be in there and closing them all up after each other. And this is very simple. Now there's one function that you might think it's helpful called append KV, because appending a KV might be really useful. If you have already an existing chain, you might want to append to the end of the chain or append to the end of the list. This is what I'm going to do. I'm going to say inix append KV. Append KV is going to get the same parameter than new KV. The only thing that it now requires as well is it's requiring a root. inix KV pointer called root. And now we can append to that root and start appending until we find the last one. Now, how can we append to the root? That's going to be quite simple. I'm going to check if my root has a next KV. And if this is the case, I want to set my root. I actually want to modify the pointer that I've got, and my root is now going to be equal to the next KV. Now, you could also create a copy if you would require the root, but we don't need the root. We can always set this to the next one. Now, one thing that I want to do is actually I want to have this as a while loop. So actually, as long as we have a root, so as long as, or not like that, as long as our current element has a next KV, so as long as the root has a next KV, the root is going to be overwritten by the next element. So we kind of like modify root until the root itself does not have a pre-successor. So modify root, always assign root to the next element until we don't have a next one. We're kind of like walking to the end of the list. And now root is at the end of the list, and we can just say root next KV is equal to INIX new KV. So now we are assigning the next KV to a new KV, and we are giving it a key and the value here. So find the end of the list, and then append to the list by assigning the next one to a newly created element. And that's everything we need to do here. We iterate over this. This is called iterative. You could also do this differently. You could do this as with recursion, actually. You could do something like if root next KV, you could call in INIX append KV for root next KV, key and value. And you could say else if we don't have a next one. Then you could also say this one. So if you would write your function like that, this now would be recursion as well. However, I personally tend to avoid recursion where it's possible and doesn't make the code bigger because recursion is limited. As I told you, every function call is going to be on the stack. If you're calling a function, it's going to take a continuous or a specific amount memory of the stack. And the stack has a certain size. Now, if you have a really long list, everything that is doing it recursively is going to have a limit. It's going to have a limit of the stack size because we have a limit size on the stack, and recursion is always populating the stack. I mean, in this case, it really doesn't matter because the close function does use the stack, so we are already game over here. We would need to make this completely without... we would need to do this completely without... recursion if we would want to have this 100% safe. But what I do personally, if recursion doesn't make sense, like closing, the function is with recursion way easier than it would be without recursion. Here it's just a simple while loop, like basically just two expressions if you don't count the brackets. And this is simple and easy to understand. We don't need to have recursion in here to make this understandable, right? So that's totally fine here. Okay, so now let's do the same thing for the section. So let's create a new section here as well, and we also want to close the section. This is actually quite similar to what we had previously. Section itself, we can actually copy the code from above here, and we just need to replace this. I'm lazy. This is why I do stuff like that, even though I'm like replacing like all of that. So I am renaming this to section. So section is equal to malloc size of section. Now the section name is going to be equal to strdup. There it is, string duplication of the name, and the section itself, section first KV is going to be equal to 0. So we're not going to have a first element in a section. And then the next section is going to be null, so that everything is good. And then we can return the section. So very simple. Section itself, duplicate the name. We don't have any key values in here. We don't have a next section. Done, creating a section. Now closing a section, this one is going to be a bit more involved. The first thing that we're going to do, of course, is again, if section has a next section, we want to INIX close section, that one first. So section... next section. Same thing that we had previously. First go into recursion depth and clean up all old sections. Now we need to clean up the members. What members do we have? We have the name. We can free this with calling free. Name is very simple, just a string. And now we just need to free the first key and value. Or do we need to do it? And then we can free section. And now you have produced a nice and easy memory leak. What is the memory leak and what is the issue with that memory leak? We have actually two issues in there. First of all, this function could fail. If we don't have a key and value pair, one of them, if the section is empty, then this function is going to fail. It's not going to be empty and because how our SAX parsers build up, but just to teach you clean code, this one could be null because it's initialized to null. So the first thing that you actually should check is if that one is populated. So if the section has key and value pairs, then you want to free it. One bug, done. Another bug introduced, so other bugs still not solved. This is introducing you a fine memory leak. Why is that introducing a memory leak? Well, it's introducing you a memory leak because key value pairs are created by calling new KV. And new KV is not only calling malloc on itself, so it's not calling malloc on the pointer that it returns, it's also calling malloc on the key and the value that are in here. And if you don't free them, close it please, if you don't free them, these are never going to be freed and you're going to have a memory leak. Same here with the next KV. If somebody called append multiple times, you're just going to always remove the first one. So instead of actually freeing the section here, freeing the actual member here, we want to call inix close KV. If you're calling inix close KV, key values are properly closed and all the dependencies, or we're going to go into the full recursion depth and everything is been cleaned up correctly. Now, boom. Finished cleaning up sections. Is it everything that we need for sections? No. We want to append sections. Same here with inix kv. So I want to be able to append sections as well. So void, I just copied the signature, but let's say void inix new section. No, it's not going to be called new section. It's going to be called append section. I want to have an inix section pointer here, root and name. So append a new section. All right. How can we implement that one? Well, actually completely similar to what we had previously. While root next section. So as long as we have new sections, root is going to be equal to root next section, so that we are now at the end of the list. And then we can say root next section equals inix new section with the name. Done. Finished. Correctly initialized a new section. Is that enough for sections? You would think yes. I say no, not enough at all. What would happen if you now want to try to append a key value pair to the section? Well, of course, this one needs to be concerned as well. So how can I add a new section to the so how can I add a new key value pair to that section? I would need to implement this manually. However, I don't want to implement stuff manually. I want to have everything nicely done. So appending a key value pair to a section. Okay, so void inix append kv, or just append kv to section. So append a kv to a section. So we're now going to get the section itself, so the section to where we want to append. And we're going to get a constructor pointer key and a constructor pointer value. So now I append kv, but differently for the section. Now, how is the implementation going to be? Implementation is quite simple. We have two cases that we need to check. First of all, the section already exists. We already have a first key value pair. If we already have a key value pair, we can just say inix append kv. So we can now append a kv. We have the root here, we have the first kv, and we want to append the key and the value to that one. So we are going to append to the first one that we have. But what happens if we don't have a first one? Well, we have to create a first one. So the first kv is now going to be equal to inix new kv. So if we don't have one, we need to create a new one. If we already have one, we need to append. So section here, key and value. We have a section here. So we can append to that one here by append kv and new kv here to initialize the new one. Appending, new one. Very simple, very easy to do. Is that everything that we need for the section? Well, seems like it is. But now we need our root functions that we actually want to call on a daily basis. And our root functions are going to be to add a section to the actual data object. Now, this function is going to be a special one because this is going to operate in different modes. So inix assert, or not assert is used in different terms. Let's call it ensure. Ensure section. Inix ensure section. What is that function going to do? That function is going to ensure that a section exists. How I'm going to do this? Inix section. No, not a section in general, but you're going to give it a name. So const char pointer name. So this is going to ensure that a section exists. And the section, of course, needs a context on where it exists. And the context where it's existing is going to be the ini data here. ini_x data data. ini_x ensure section. Now, this function should ensure that the section exists. Now, if a section already exists, fine. If it is not existing, ensure that it now exists. How are we going to do this? Well, I'm going to have an int section exists, which is going to be 0 or false. So by default, the section is not going to be in existence. Now we need a starting point, ini_x section pointer section, and this section is going to be equal to data first section. Now, what we're going to do is, while the section pointer is valid and the section does not exist, or no, we can stop this differently. I don't like big whiles. While the section is not existing, while the section pointer is valid, we want to iterate over them. The last thing that we want to do is we want to assign the section to be the next section. So this is going to be our loop. As long as the section is valid, actually we could do this even in a for loop, right? I said that I like for loops. So section is going to be equal to data first section. Then we're going to say section pointer is valid, and section is going to be equal to section next section. So this is iterating over all sections. And now what we need to do is we need to check if we found the actual section. How can we do this? Well, I can write this by checking our strings. So if string compare, string CMP of our current section, name, and the name we are trying to find, if this is equal to 0, so they are the same, then I'm going to say section exists equals 1, the section is now existing, and I'm going to say break to break out of the for loop to continue on, because if we found it, we no longer need to check if it's already there. So this is basically here, check if section exists. Now, if the section already exists, everything is good because we want to ensure that it is existing. But now we basically need to insert section if it is not existing. So if our section is not existing, we need to do something. So if section exists, not section exists. So if our section does not exist, we need to do something. Well, actually, again, we're going to have two options. First of all, our data has a first section. Do we have a first section? If we have one, great. We're going to say ini_x append section. Now we can append a section. We can append a section to the root section, which is our data first section. And we want to append the name. So this creates a new section. Now, if the first one is not existing, we want to say data first section equal ini_x new section. We'll create a new one here, and we have a new empty section. Now, this is going to create us a section if it doesn't exist. And this is now going to ensure us that our section is existing. And this is actually now nearly everything that we need. It's just one function that we need, at least to do the parsing stuff. So we need another function, ini_x append kv. So is that actually, okay, this is append kv to, how do I want to call it, to section? Actually, ini_x append kv to data. So ini_x append kv to data. Actually, did I? Okay, I have now always added the underscores, and I have completely violated how I write my functions. This is something that you probably don't want to do. I just used the ini to separate these one, and these one were all in caps. But since these are internal, it's okay. On a public API, you would never want to mix and match this style with this style. I basically have screwed up everything, but I don't going to rename all the functions. So I'm going to show you bad practices here. Haha. Okay, so data, const pointer name, const pointer key, const pointer value. So this is basically our nice function that we always want to use. Append key and value to data. Now, how's that function going to work? This function needs to first ensure that the section exists. I call this now name. Let's just call this section. This is a bit more meaningful. Section and this. So basically what I want to do is, if I want to append a key value to a data, I want to first assure that the section exists. How can I ensure that the section exists? Well, I'm going to give it the data in here. and the section name. And this is now gonna check if the section exists. And it is also gonna append it if it's not existing. Now, this function has a big design drawback. The big design drawback is that we don't get the section. Now, what I would need to do is I would need to write a full custom owned for loop that finds the section in question to give it to me so that we can append a key and value. So what I really want to do is I want to rework that function from above here, and I want to rework it so that it returns me the section that has been ensured. So the section that has been ensured should return itself. So it's going to return the pointer, and this one should now ensure that the section exists. Now, instead of doing it like that, we want to call this found section, so that we found a section, and by default we didn't found a section. Now, instead of setting section exists, we're going to set found section equal to section. Now, basically, if finding now succeeds, we will have the founded section in here. If we don't have it, we need to append a section. Now, as you can see, the append section function is not giving us a pointer. That is something that we want to do. The ini-x append section should also give us the pointer to that section that just have been appended. So we need to revert that function as well. So ini-x append section needs to return this as well. So append section should return us an ini section pointer here as well, so that we know what it appended. Just should be append section, append section, append section here. Now, basically, we're going to say in equals new section, and we can then just say a return root next section, so that we return the section that we just appended. Okay, simple as that. Now this is going to pass through until here. Now the only thing left to do here is say found section equals, and now you can see that this actually works. We can do this double assign and see this is working from right to left. So ini-x new section is going to be assigned to data first section, and this one is then assigned to found section. So you can do this in one line here that all have the same value populating from the right to the left. So right name evaluated, populated to everything on the left, so that everything is set correctly. Now the only thing that we need to do now is we just need to return the found section here so that we get a section out of that. So now we can have the ini-x section pointer section equals, now actually a section name is already there. Let's call this just as here, inix ensure section. So this function is now ensuring us that the section is existing. If it's already existing, it is not going to create a new one because sections should be grouped. That's the whole idea here. And we now can ensure that this is working. Now the only thing left to do is to append a key. So if the section is existing, I'm checking this because we are mallocing here, and if this malloc is failing, we might get a null pointer. So I want to make sure that s is checked here. Like here, new section can be a null pointer, and then this is returning a null pointer. And if we have a null pointer here, then this found section is null pointer, which we are returning through. So we need to always make sure that this works. Now, if the section is existing, we are now ready to append the key. So what we could do is we can say ini-x append kv. And append kv is very simple. We need the root kv. The root kv is going to be a section first kv. Now the section first kv might not be existing. So actually I want to check if the section's first kv is in existence. And if it is in existence, I want to append to that first kv the key and the value. Now, if it is not existing, I need to create a new one. So the first kv is going to be equal to ini-x new key value with key and value, so that we have created a new root. Now, this has one big drawback, this function. And the problem is that we are not able to actually check with ini-x append key that the key is not already existing. If the key is already existing, I want to override it. How could I override the key? I need to first get the key. So I need the function to get a key. So we have new key, append key, close key. Maybe I want to do a bit of maintaining here. Oh, I'm not zoomed to the left. That's not good. I want to quickly differentiate these ones so that they look nice. Now we have new append a close, so now let's also write a get function. So ini-x kv pointer, ini-x get kv, and we're gonna get a kv by INIX section from the section and a const char pointer name. Or actually not a section. Let's do this as an INIX kv root. So we have the root kv and we're trying to find one. Now we're going to do this with recursion again. So how we're going to implement this? So first of all, we need to check ourselves. So if string compare of the roots key and the name, so if the current one, if we are the current one, if this is good, we are returning the root. We found it, we are on the root. Now we have a few more cases. If we could do this with else if, but it really doesn't matter because if we are inside of this if, we are returning and we are directly away. So another one would be if we have a next section. If we have a next key value, not a section, a next kv. If we have a next kv, we're gonna return INIX get kv. So we are getting a key value from the next kv with the same name. So if the names match, we are returning the current one. If we have a next one, we are returning get kv again, but with the next one now. And the only thing left to do is have the default case. By default, we are returning null because we didn't found a kv. This is happening if it is not matching and we don't have the next one, which basically means that the kv is not in the list. And then we can return null and we have properly found the kv. Now we can simply do this like that. I can simply do this by, how was it called? I can go down a bit. So append kv was appending a key value, and what I basically now want to do is I want to check if I can find this now. So INIX kv pointer kv equals to INIX find kv? No, get kv. Get kv, so we want to get a key value pair. The root is going to be my first kv and the name is going to be the key. So we are trying to search for the key. And if we found that one, we don't need to append it, we need to replace it. If it's not existing, so we had null, we need to append one. If we found it, we need to alter it. So the first thing that I want to do is I want to free the old value. So I want to free the actual value. The key is the same. And the new value is going to be equal to the strdup of the value. So now we basically replace the old kv with the new kv. Now one thing, actually we should, if we would be 100% safe, always check if these strings are actually there. So something like if kv value, then free it. I haven't added this, I think, in the other ones, but I should add them in the other ones actually. Everything where we freed names, something like that. We always want to make sure that they exist because string duplicate can return null pointer. So if we would want to write our library 100% safe, we would need to check them always above here. Right, so existing. The other freeing, we should then also, maybe, I think we actually, I think yes. Okay, so it's, oh god, I was a bit on the wrong track here. Okay. Alright, so, okay, these two ones, we need to do them later here. I still want some to do up here, but we're going to do this in a second. Now, let's go back to the append function. I think append now is finished, so now we can append one. We can ensure that the section is existing, and then we can correctly append to it. This should be 100% correct. And now actually the only thing that we need to do, or actually what you can already see, is that this signature, INIX data, section, key, and value is now exactly the same signature than our callback. Our callback has the same signature than what we now just added. And this is actually what we have done. We now have completely constructed the behavior of our callback. So actually our callback can go, and we can replace it with the INIX append kv to data. So this is now going to append key values to the data with the section name and the key and the value names. It's going to find a section, it is going to append to it. Now the only thing that we now need to quickly implement is that one. If the data is in existence, we need to quickly check if data first section is existent, and if the section is existence, INIX close section. So we need to close the section here. In the cleanup, we haven't implemented this yet, as well as the new one. If it's new, we want to make sure that the data first section is equal to null. And actually, did my function check for null the ensure section? I think, yeah, ensure section, found section, yeah. It was ensuring for new. So actually, this should be now everything that we need to DOM parse our library. Now we should have a proper DOM element if we parsed everything correctly. I have no idea if it works, but we're gonna see. Now, first of all, I don't need my data ready ones, but I might need them. I might keep them in here. We might later on add a functionality to the DOM ones to actually SAX it out again. So our DOM API might later on have enumerate SAX function that takes the same callback than the SAX, and so that we can use this one as well. So I'm gonna keep them in for now. The only thing that I want to do here, the callback, we could actually keep them as well because we might use them later. However, now I no longer want to use the INA parse INA from file. Now I actually want to use the INAX one. So instead of INA parser, I'm going to include INAX, which is still going to leave them valid because they are in there as well. So INAX data is going to be the return value, INA data, and this is going to be equal to INAX, and now you can see we have a hell of a lot of functions in here that are all not usable. We should actually, to be a bit more concise, we should have added an underscore for all the functions not exposed. However, that's not the point. So INAX parse INA from file, file path. How did I call this? File. Callback. Oh, did I just use my? Okay, it seems like I just used my argv position 1 and then my log file like that. All right, and this should now parse our data, and if the parsing was successful, we want to say INAX close the INA data so that data gets freed correctly. And now let's make a breakpoint here and maybe a breakpoint here so that we can check that we made everything correctly, including no memory leaks. Pressing F5 and okay. So the string duplicate function that we use is also deprecated. We should use underscore string duplicate. Okay, so this is just with underscore. We can actually do this like that. If you're marking this, Control F that, press that arrow down here and say replace with underscore string duplicate current document, replace all. It is replacing all that functions calls that were incorrect. Okay, yeah, it replaced that one as well because it was like kind of matching. Now this should work, hopefully. Let's see. Okay, but we have a few warnings. Let's see what the warnings are. Incompatible type, INI section pointer to INI. Okay. Incompatible types. This is not right. I don't know why it's saying that. You can see that they are the same types here. Okay, some madness going on here with Microsoft, but actually what we have done is correct. So now let's test this. Let's press F5. It's actually not testing, we're just trying it out. I'm on release, which is something I don't want to be. I want to be on debug actually. So let's quickly stop this and go back to debug. Press F5 and see what we got. So debug. So first thing that I want to do so that we can see potential memory leaks is I want to enable heap profiling. So memory usage, heap profiling. And what I want to do now is I want to take a snapshot. This is now a snapshot of our current memory. And if I now click continue on and take another snapshot, we could see that we have memory allocations. Actually, you can see that we have 21 memory allocations, which seems kind of right for what we have done. 21 memory allocations. We can go in a second in here and test this and see if everything works. And what I expect now after I've hit continue, I would expect that we have 21 freeings. Actually, we just had 20. So we might have a bug in here. Oh yeah, but we had one allocation. Okay, so you can see that we had 21 allocations here and one allocation there, and we had minus 20 here as a total and plus 21 here. So we had 21 here, we had 21 deallocations. Minus one allocation is a balance of 21 of normal 20, so this should be good, but I'm gonna debug this in a second if this is all good. Let's first take a look at if our data is actually working. Now, since we are Visual Studio guys and Microsoft guys, we can just take a look at the structures in down here in the debugger. So INI data is what we care about. So as you can see, we have a first section that it seems valid. Now the name of the section is owner. Maybe I should open up the file so that we can see what's going on. Config.ini. So this first section name is the owner. That is correct. And the first key and value has a name of has the key of name, which is that one here, that's correct, and the value of John Doe, which is also correct. We also have a next key value, which has the key of organization, that's correct, and the value is ACM Widgets Inc., which is also correct. And the next key V is null, which means it's the end of the chain, since it's the last one in the section. This seems legit. Now, let's go to our first section and take a look at the next section, and we can't. We can't see it because Visual Studio doesn't like how we do stuff. Okay, we can solve this. This is now just because Visual Studio is a bit cocky with our code. Basically, it is not liking that we are using the INI KV pointer here for the, but why is it allowing this for the first KV? I know, but what you can always do, like to make Visual Studio not being a total dickhead, is by adding the proper struct names and pointers. Visual Studio does like them, but I think this is the issue. But it's a bit odd because sometimes it detects them and sometimes not. We're gonna see, maybe we also have a bug in here. Could also be, but this is like the first thing that I would suspect might went wrong. But still, the next section, I mean, the pointer is here, but it is not able to inspect this. Now, what we can always do if something like that doesn't work, I don't know why the next section is now, why I'm not able to expand this, but what you can do is you can go to watch, and I can cast this to INIX section pointer, and this is now going to give us another section here, and this is, as you can see, it's working. I don't know why the debugger is a bit cocky about this, but as you can see, it works because now the name is database. The next section is null because we don't have any succeeding sections. The first key value is server, and the value is the correct IP address. The next KV is port, and the next value is the correct port. The next KV is file, which is the correct data payload, and the next KV is null. So it's kind of working, but on our locals, the debugger didn't like to display that correctly, which is not understandable. I mean, like the struct pointers, it's all... Or did I forgot a pointer somewhere? Struct? Oh, alright. I just forgot the underscore while refactoring that. Okay, so maybe this now helps. Does that help? Yeah, that helps. Now we have the next section in here as well. Okay, so that was the issue. So it was the same that I expected, but I refactored it wrong. But you can see basically that all the data that is in here looks good. Now we can assert that our memory works by taking a look at what memory allocations we do. So heap profiling, we're going to take a snapshot. I'm going to click continue on, and I'm going to take another snapshot. And I'm going to inspect the snapshot by clicking on it. And we now can go to stack and see where we allocated data. So I personally just care about something that I do on my own. Let's maybe make this a bit smaller here so they can see this. It's inside of invoke main, and it's inside of this INIX parse INI from file. Now I care about these two. You can actually see that these are now coming from the DLL. Since we have a static library, you can see that these calls were made by INI parser.dll, while the other ones were made by INI explorer.exe. You can actually now see where this has been issued, this call, and I personally care about the call of INI parse INI. That one is having 19 allocations. These are the 90 ones that are inside of that function, so they're basically append to key v, and you can then see that append to key v called append, which called new that called in this case malloc, so it's down there, and zero section, which called append, so you couldn't like count them all up if you are taking a look at our new functions. 2, but I don't care about these. I just care about what like the callback call, which is this INIX append kv to data, which is the same than like the parsing function and the parsing function mallocked 19 times. So 19 times it called malloc. So we have 19 allocations, and that's the number that we care about. Now I can close this profiling, click continue, take another snapshot. Now I can go into that one again, go back to the stack, but no, that's the wrong one. I care about what have been freed. Is it not telling us? Oh, there it is. Invoke main. I pass. No, I don't care about these ones. Why can I not see what has been freed? Because it has allocated something. Can I take a look at that one? Yeah, that is the right one. So I actually need to click on that arrow, on that -20 at the arrow, which is telling us what has been done. This is showing us a balance that I want to take a look at this. Now, if I would navigate down to my main again, I care about these calls. So you can actually see which calls had been unrolled. So we can actually see that our ini pass from file with our ini parse and our ini-x append key to data. This has been unrolled by having -19 in here. And you can also see ini-x new has been unrolled one time. Actually, I didn't show this to you, or I didn't talk about this. This was the call in here, ini-x new. We basically had +1 in here. And inside of our parse ini, we had +19, so +19 and +1. This one has been done locally. It's shown in here, but it has been already cleaned up, or I think it has already cleaned up, or we had already memory leak in some older video. But I just care about that one, +19, and about that one, +1, which is exactly which has been unrolled here, -19 and -1. So we don't have any memory issues in here, which means that everything has been parsed correctly and our DOM parsing works. However, we are still not done. Why are we not done? Because DOM parsing makes totally sense, but it doesn't make sense if you don't have a way to access the data. And if you would take a look at our API, the available functions to us are currently just these three: path from file, parse, and close. These are the only three that are available. Now, what I want to have is I want to have the option to also get a key from that thing. And I also might want to check if a section exists. I want to have something like section exists. I want to have two functions. So, actually three. I want to have a function section exists, key exists, and get key. That's what I want to have. Okay, so let's implement them. ini API int ini-x section exists, which of course needs the data and a const sharp pointer name. So data and name, and it should return a 0 or 1 depending on if it exists. Need the same one for key. ini key exists in a section, and we have key there. And I also want to get something. Get ini-x get section and key. And this is returning a const char pointer. We should not modify that one. That is from our API. So the client should modify it to get an actual value. And this makes our DOM API feature complete. We could think about more functions, but yeah, let's just create these functions. All right, section exists. How does section exists work? Currently, it doesn't work at all because we don't have a function that can handle this, but we already have the code. We have the code for that function, or what it does. We have the code for it in our, where was it? Ensure, append, kv to section. Where is it? Ensure and section. Yeah, basically that one. That is the code to find a section, but it is inside the ensure function. So actually, what we want to do is we want to factor this out into its own function. So it is going to be called ini-x new section append. Okay, there it is. It's going to be called, actually, yeah, let's do it here. ini-x section pointer ini-x get section. And this is going to get a root and a name. And this is going to give us the section in question. Now let's create a definition here. And let's copy over the code that we had. Is it above or is it below? It's below, of course. Okay, so basically that is what we want to get. So let's copy that one, and found section by default, it's not going to be set to null. Now it's going to be set to get section of our root, so data first section and name, and of course this is only allowed to happen if the first section exists. So first section, if that one exists, I do wanna do that call, close the bracket here, and then it's gonna be set. Now we just need to implement the function above here. So found section, and this is going to be equal to our root by default. So section is going to be equal to root, and as long as the section exists, we're going to go to the next section, and I'm going to return the found section down here, and this should now allow us to get a section. Now, what I basically want to do is I want to return data first section. So the first section must exist, and that one needs to return a thing. So we have a Boolean expression. The first Boolean expression means that pointer. If that is true, so that section exists, we're going to go to the next one. If this is false, it's going to directly abort. If this one is false, it's directly returning. It's directly saying, okay, the Boolean expression, it can't be true. A Boolean expression can never be true if the first element is false. So this is working from left to right. First element on the left is false. I'm not going to continue on. So basically what I'm doing here is I'm doing my checkings that I need to assert for that call, so that the actual object that I'm passing in is valid. The actual pointer that I'm passing in is not null. That one I need to assert. This function is going to work with a null pointer, and that one is checking that. And if this is false, it's directly returning. And if it's true, it's going to continue on, take the first section and search for name. So this one should now give us if a section exists. So we could try this out. Actually, no, let's not try this out because we're exporting something that's not been implemented. And this should in theory fail. But it does not. Okay, so if we don't use it, it doesn't fail. Okay, not to be fair, it's okay. For me, it's not an issue. So what I could do is I can say F1 for found one. So found one. I do want to find the owner. So for example, INIX section exists. So INI data, and the section is going to be owner. So does that section exists? Server, I think, was the other one, and blob, which shouldn't exist. So found 1, found 2, and found 3. Let's make a breakpoint here and see what we got. So found 1 is 1, and the other ones are 0, probably because it's not called server. Yeah, it's called database. That's right, it can find us now. But if I change this to that, owner should be 1, F2 should be 1, of F1 and F2 should be 1, and F3 should be 0, which is exactly what it is. So this is working nicely. Now we need to continue on and write a bit of more code here. What do we also need? Key exists. All right. How does key exists is going to work? Well, the implementation is going to be quite simple. First, we need to find the section, and then we need to find the key. So what I'm basically going to do is INI section, pointer, section, or let's just call it as, equals get section of the root. So data first section, and if my section exists, I can work with it. But before we can do that, let's check if data has a first section. If data has a first section, we're going to try to find it, and at some point we're going to return 0 because it's false. And if we are now found the section, we can now try to find the key. So INIX get KV. To get a KV, we need the root, which is the S first KV, and this is the key that we want to check. And what we want to do is, if the section has a first KV, then I want to return INIX get KV. Now INIX KV, if that pointer is valid, it is returning 1. So now we should also be able to check for a key. So let's try this out again. So I want to always check on the owner. Key exists. Key exists. And key exists. Now the owner is going to be having a name and a company, I think. Or was it called organization? And the blobby. Blobby. because Bloby is not in existence, but I think it was called organization. Yeah. So I would again expect F1 and F2 to be 1 and F3 to be 0. Let's see. Let's see. F1, okay. So that didn't work. Okay, I know why it didn't work. Because it's not a Boolean expression now. This is now returning the pointer as an actual pointer. It's not converting this to a Boolean expression. We can force it to a Boolean expression by doing something like that, by just making this logically, by saying one and this should convert this to a Boolean expression. I don't know if this works on release or if the compiler tries to optimize something, but this at least gives us that as one. I don't know why organization is not working. So this is a bug. We need to find why it doesn't work. Organization did not succeed. So we need to debug why this is not working. Okay, so let's try debugging this. By F11, jumping into indet here. First section exists. Okay, so they don't care about this function, it's probably working. This one should go in here, and first KV should also be good. Okay, so now let's see what we got by get KV. So, let's see. Okay, but this is not it's not same then. It's not the same than John Doe. So that's good. But our root does not have a next KV. Okay, so John Doe is not the root. Okay, why is the organization no longer in here? Okay. Whoa, okay. Why is our chain not complete? Why is the organization not being parsed? It was in previously, but it is not in there now. So we have a bug in some of our code. Let's quickly jump out of that and let's take a look at this section. So the first KV is John Doe, but the next one is null. So why didn't we parse the next section? Okay, so actually we have an issue in parsing, but we didn't have this previously. So by changing, okay, so this can just have, this can only have one reason why this is not working, because we just changed one function that was used for parsing. We changed our function called, change the function, the ensure function. INIX ensure section. Close section, ensure section. We changed that one. So we set found section to null. And if we had the first section, okay, good. So we need to do it like that. We need to, of course, assign the found section to get section. If we don't assign it, it can never find it if we have a first one already there. This is why it was not able to pass the second value. Okay, this now should render these functions useful again, and we should now get 110, which is exactly the case. So we fixed that bug, and key exists now works. Okay, this just leaves us with one function that we need to implement, INIX get. No, that is not what I wanted to do. This is definitely not what I wanted to do. I accidentally created like this hint file. Delete that one quickly. Alright, so create that one in the C file, and let's take a look on how this works. Alright, INIX get. We need to get the data that we want to have. And how are we going to do this? First of all, the last thing we're always going to do is return null if we had a failure. So if data first section exists, INIX section, okay, no, not in caps, INIX section, pointer s equals INIX get section. Now section needs a root, data first section, and the name is going to be the section itself, which is giving it a section. And if we found that section, we can continue on. Now we need to check that the KV pair is in existence too. We can directly do this in that if the section exists and the section has a first KV pair, so the section is not empty, then we want to search the KV. So KV is equal INIX get KV. Now we need the first KV or root KV, which is that one, and the name is going to be the key. And if the KV exists, I'm going to return the KV's value. Simple like that. And now this should give us a string. This should give us now the data inside the INI. And this actually concludes everything that we need to implement in a proper INI parser, in a proper DOM parser. No, I did want to implement one function so that we can use our SAX again. So let's try to find it out. INI get. INI get. Now INI get. Now of course these need to be const char pointers. Let's call this owner name. My idea on how it's written. Const char pointer. Owner orga for organization. Const char pointer owner blobby. Actually just owner blob, because then it's nicely formatted like that. And now I would expect to get the actual data from there. And can we take a look at this? Okay, owner name, John Doe, owner organization, ACM widgets, owner blob is null. Exactly how we want it. Now, we could do also something which gives you a default value, but I'm not going to do this. Now, what you could do, for example, pass in another parameter as a default value and then return this if it's invalid, but I'm not going to do this because, yeah, not going to do this. Okay, so let's remove the blob now, and now let's add a bit of printing. So printf, this application is operated by from that. So this application is operated by owner name, by owner organization. So I can print that. Then I'm gonna close this, of course, and I'm done with it. So now that's nice. This application is operated by, let's maybe do another printf and say classical SAX parsing following now. Like that, so that we have a classical SAX in here as well, so that everything still works, and classical formatting. Of course, it's not going to do anything yet, but at least now I should get something. I would like to clear that one because I am press any key. I didn't get an output. Why didn't I get an output? Go on, let's close this. I have the suspicion it didn't do what I want. No, it did do this. This application is operated by John Doe from ACM Widgets Inc. Okay, so nicely printed our configuration. Classical SAX parsing following now. So now let's do the SAX parsing to make this feature complete. And this is not going to be called parse, this is going to be called enumerate. So I'm going to call this INI API void INIX enumerate. And this is going to get a INI callback. Of course, it needs data first, so INIX data, here data, callback, and then it's going to get a void pointer user data, so that we can properly operate the callback. And now we just need to implement it. Come on. And hover over this, create this in here. And we're going to properly implement this. Now, how are we going to implement this? With a simple for loop for INIX section pointer section equals data first section. Section needs to be valid, of course, and section is going to be equal to section next section. So this is going to be our for loop over that. Inside of that for loop, we're going to have another for loop of INIX KVs. No, INIX KV pointer, KV equals to section first KV needs to exist, and KV is going to be equal to KV next KV. So this will operate over all valid sections and all valid KVs. The only thing I now need to do is I need to store my pointer. So const char pointer section name is going to be, of course, equal to the okay, I can actually operate this down in here as well. I don't need to do this like that. So actually what I just need to do is I just need to call the callback with my user data, the section's name. So section name, the KV, the key value, and the actual value of the data. Now I have replicated my standard SAX parsing with my DOM API. It's looking way cleaner, and you're also getting, if you had in the SAX parsing, if you had duplicated sections, you always would get the sections in here and this. But yeah, like if you have, no, not duplicated section, sorry, duplicated key in section, if you would have this into the SAX API, you would get the value twice, and here this is already filtered out for you directly at the beginning. It's something that we can check in a second now as well. But I want to quickly call this enumerate here so they can see that it works. INIX enumerate, INIX enumerate here to enumerate all data. So the data be the INI data. Now the callback is going to be the, what did I call this one? Okay, just callback, and I don't need user data here. Callback like that. And now this should also print it in the classical way like we were used to it. Yeah, classical SAX parsing, owner named. Okay, now you can actually see, yeah, but I think it's the same. Did I output it is the same like with this? I think yes, because it's like outputting the style for each. Yeah, I think it was the same. Yeah, John Doe, ACM widgets, IP address, port, payroll, that. It's all working. And of course, if I switch back to release, it should all still work the same. And if I run this, we just should get a different output here because it has a different parsing with the SAX data. And now we can play a bit around with that. I could, for example, now override John Doe with my name, so Ludwig Fusel. I'm not daring to write the Ö, or maybe. Can't see, shouldn't break, but it should also not look nice. And now you would see this operated. This is operated by Ludwig Fusel from ACM widgets, even though I'm not from ACM widgets, of course. And also here we just get one owner name, and we had two in here because it was like overwriting that here. And also now what also of course works is like section clashing. I mean, we haven't tested that really, but of course this works as well, like Lelophone. If I would do this like that, Lelophone of course works as well, right? It doesn't overwrite all, the sections will still be there, but if you duplicate them, it works. The only thing that this library currently cannot do is bashing data together. Why can't it bash data together? Bashing data together would be if you have two INI files and you would mesh them together. This is currently not working, but this is something that I want to add now as well, because it's so easy to add it. You can see that by default, where is it? INIX.h. By default, we got our INIX data here. We got this from the parsing function. This is the only thing that we need to change. Actually, if we remove this and replace this with void and add these as a parameter. So if I would add the data here as a parameter and the data there as a parameter, then we would now be able to now use this multiple times. So use one INIX data struct for multiple calls to the parsing function, which would allow us to parse multiple files together. This might be useful if you have like a default file and you want to then load a user configuration from the users directory. The only thing that you would now need to do is to have this one lonely function up here in our public API and expose this with the INIX API. And this is then now going to return you the object. And now you would just need to modify the code. So go a bit up here. So that this is concerned in here as well. Data in here. And now instead of allocating them here and returning them, we are just calling the parse function. But of course, these are void functions here. And actually what you could do, you could actually now use the preprocessor to call the function for you. You could actually use the preprocessor for these ones, but I'm just leaving them as an API here. Of course, this requires modifying our C function. This is now going to be equal to INIX new. And this one is going to travel inside of here. And now it's also going to get the INI data here so that it parses directly in this INI data. Then we can print our stuff and then later on close it, of course. And if I do this like that, it's going to do the same thing. The only thing that I would now be able to do is I would now be able to do also have a default.ini file where it tries to do it. So I could do something like default.ini where it tries to load defaults, and after that I'm bashing over my user configuration. So if I would do this like that, I would need of course to create a default.ini file. Let's do this. New item, utility, text file, default, default.ini, and what I can now do like is owner, name, your name here, and organization, your organization here. Something like that, right? Would be easy to do. Your name here, your organization here, organization here. And if I would run this like that, it would make any difference? It does, because I have okay, organization is written with Z. Organization, really? What if I do it like that? Now John Doe and ACM widget is stronger because it gets meshed over these default ones. But if I would now, for example, in here replace the John Doe with the hashtag, and I don't know if it's working like that. Yeah, if I now replace the John Doe, comment him out, you can see your name here, for example. Or if the owner isn't not working at an organization and he doesn't fill that in, your organization here, or you could do something like default one, say not available, no organization available. Would say organization is not available, is operated from form, okay, a typo in there, from not available, and only if John Doe decides to put his organization in here, it's also going to be used, right? So that operates like that. Let's quickly fix the typo here, from John Doe in there. So yeah, that's it. INI parsing done correctly. Now, with a DOM API. DOM API, as you can see, if we take a look at the source code, not even that long, like 240 lines. If I would take a look at our default parser, it is like roughly the same. Yeah, a bit shorter. But you can like see, really, there's no big deal behind doing stuff like that. It's no magic. It is just on how you work with pointers. And this is why I wanted to make this video, even though this is like 1.5 hour long, even more than 1.5 hour. But I think it's useful for you because you kind of like see how you work with that. And I also wanted to have like a video where I completely write some production code from top to bottom so that you can actually see how you would work with that. One thing that I'm not happy with the video, but I'm not going to redo this just because of that thing, the underscores. These are not my naming conventions. I could rename them quickly because I personally don't like it. Section exists should look like that. I mean, Visual Studio has tools to automatically do this, so... And magically everything is now in the correct format. I'm a bit more happy if I do this in the correct format and push this to Git with the correct format. And since Visual Studio makes it easy to rename them, it's simple. Okay, so thank you for watching. Hope this was useful. Hope you learned something, and hope you are thrilled to the next video. And hope you are thrilled for the next video where we're gonna clean up and do all of that C work. Hope you're thrilled for the next C video where we're going to talk about everything that has been lost during the series, because we have a few things that we haven't talked about yet and I want to quickly revisit them so that you know what they are before we are moving to C++. So yeah, thank you again for watching. See you in the next video. Make sure to like and subscribe and have a nice day. Bye.